My name is Jose Solomon, and I am an AI engineer with the Fields App team here in Palo Alto. The focus of this session will be on the impact of batch size on training a model that is deployed to the IPU. The topic of batch size adjustment when it comes to deep learning optimizers is very nuanced, and many conclusions are highly correlated to the model being trained. The focus of this session will be on how to leverage the IPU's fine-grained compute capabilities to use simplified optimizers at relatively low batch sizes to perform tasks that would require much more complex optimizers if one were to have to use larger batch sizes. If we compare Atom Optimizer to Mini Batch GD, we see that Atom has two tuning variables for each trainable parameter, so as to allow for parameter-specific updates. This is computationally expensive. However, if one is using larger batch sizes, on the orders of hundreds of samples, to allow for compute saturation of the underlying hardware, optimizers like Atom become par for the course. Simplified optimizers like Mini Batch GD are highly efficient and do very well at reduced batch sizes. Let's look at a conceptual loss surface that has a global minima, a local minima, and a significant spike. Let's consider a highly conceptualized problem statement in which batch size is the only adjusted parameter and all other solver elements are held fixed. We can illustrate two distinct solution trajectories corresponding to two different batch sizes. As we train our network, we see that although the solution trajectories are similar, there's a natural deviation between them as a result of the size of the step each takes on the solution surface. Perhaps we are fortunate enough to arrive at a global minimum, or perhaps we're stuck in a local minimum. But the use of a validation set, along with other elements that we monitor as we train, will help us decide where we are. Now let's say we decide that we want to take an even larger batch size, so that we can arrive at our solution even quicker. In this illustration, we reach a deviation pretty quickly. Now obviously this is a very simplified view of the issue, and there are a number of other considerations that need to be accounted for in training an actual model. So let's take a code set from Graphcore's public example repo and see how the above corresponds to something truly tangible. So we're going to focus on the MNIST example in which we train a sequence of dense layers to recognize handwritten digits. Here it has been rewritten to focus purely on the training facet of the script, but the full original version can be found in our public examples repo under Code Examples, TensorFlow, MNIST. So basically what I'm going to do here is just focus on those aspects of the script that relate to batch size values. But I would highly recommend taking a deep dive into some of these other elements like loops, IPU in feed queue, IPU out feed queue, to really understand what it means to target the IPU from the TensorFlow framework. Obviously, the scope of this talk, though, focuses on batch sizes, and so I'll just point out elements of the script that relate to that and point you towards the public example repos so that you can take a deeper dive into other elements that are associated with training this network. So basically, very standard dense layer definition. I'll just point out that we're using the ReLU activation as the output. At the output, we have a very simple network. It consists of a dense layer followed by a dropout layer and then a final dense layer, all using these size of hidden nodes for 320 for the first layer, and the second hidden dense layer has 10 hidden nodes, as you would expect for the digits recognition. We're then monitoring the accuracy, and then the loss function is the sparse soft max cross entropy loss, as you would expect in this type of task. One thing I'd point out is that in the script that you'll find in public examples, it'll be the momentum optimizer that is used. If you wanted to experiment with the optimizer I pointed out in the previous part of this talk, you'd uncomment this line and comment out the momentum optimizer so that you use gradient descent directly. We then take our loss and our accuracy and we populate our up queue. This is a very basic learning schedule, which basically adjusts the learning rate based on where we are in our training cycle. We have our loop builder, a very important concept in terms of targeting the IPUs. So I highly recommend studying what the implications are of this definition. And now we have the run model definition where we basically load our data set. It's very handy that Keras has kind of embedded the MNIST data set into its library calls, so you can directly load the data set. We're normalizing it for 8-bit representation. And here we have the batch size call. So basically, I alter this index here, but the batch size is used in a number of places in what follows. So I'm just going to try to point those out to you. We're doing some basic reshaping because the MNIST dataset basically, I believe, configured 28 by 28 pixels, one channel. And so you're restructuring it so it's all of those pixels are basically restructured as a vector. That's what's happening here. You're flattening the images out. And here's the component of the script that's related to the batch size. So we define how many epochs we're going to train the model for, and then we define how many steps per epoch we're going to take on the IPU. And from there, we're going to determine the batches per epoch. So the number of training is basically the number of training examples that we have. We divide that by the batch size. Then you take the batches per epoch and divide that by the IPU steps per epoch, which we've defined up here. And that gives you the batches per step that you're going to use when you define your loop constructor and your infeed queue, basically. So, very standard process. You create two placeholders on the host, one for the input, one for the labels, a learning schedule, learning rate placeholder. You create your data set using the TensorFlow data set construction from slices. This is the inputs, placeholders for the labels. The data set then takes in the batch size definition that we've defined up here, which is basically the one moving or altered parameter of our solution that we're experimenting with. We populate the infeed queue using the data set, and we make sure that the outfeed training queue is initialized correctly. From there, we basically create a partial call to the model. So this is the original call to the actual network definition that we have up here, where we're defining the dense layers that drop out the dense layer and our out queue. In the original script, you're going to have a Boolean here for training or inference, but I left it here just so that you would find it easily in the original script, but we're not using it at the moment because I basically simplified the script just to run training. We have inputs and labels, which is basically the data set, which we get from the data set. All right, going back to where we were, we've built that model. We now define the loop that will be used in actually training the model. And like I said previously, it's very important to get familiar with this loop construction. So I would dive pretty deep into this component of the script. We now are prepared to compile our graph, which happens in this line. We initialize our local variables on the host directly after compiling the graph. We set up a saver so that we can save the model once it's trained as a checkpoint file. We then configure the IPU. There's obviously a large variety of different configuration parameters that we can pass at this point. I highly recommend studying the documentation to become familiar with them. We prepare our outfeed queue, and we're ready to start training our model. So we summarize the defined parameters to the user, we set our steps to 0, and lo and behold, we have our session initialization line. We do our global variables initializer, and we prepare our infeed training queue. And so here we have one nested for statement which is the number of steps we're going to take per epoch, which is inside the number of epochs we're going to train for. We're going to run our training loop, and we're going to get the output of the DQ training outfeed statement here. So basically we keep a tab on how the network is training as we proceed through the specified number of epochs and the specified number of IPU steps per epoch. And we're going to summarize the output for the user. And once we're done training our network, we're going to save the model as a checkpoint file. So that's basically it. The one thing I would suggest is the batch size here is basically an argument that's passed to the dataset call. So once the dataset is structured, it basically keeps a tab of how large the batch size is per batch size call by batch call. So as it's training, it's structured. The dataset is structured in such a way so that when the session is training your model, it knows a priori how large of a batch size it's going to require to train your model. Anyway, let's take a look. I'm going to run the code just now. I am running on a DSS8440 server. It's compiling the code. I am using the popular log level info option to monitor how the IPU is doing. Things are moving along. And it's training. These are the epochs, the loss, the accuracy, and we end up at about 98.5% accuracy at a loss of 0.025. So that was one run, I believe, at a batch size of 2. And so at that point, I'll run all the different batch sizes and create some output plots that we can review together. As we can see, the lower batch sizes seem to behave relatively the same, while the largest batch size of 32 struggles to reach the same target loss at the 5th epoch. If we look at the resulting model accuracy, the divergence of this larger batch size becomes even more pronounced. This concludes a very concise review of what is really a very broad topic. I highly recommend studying the code base presented in Graphcore's example repo on GitHub for this application and others to get a feel for training models at reduced batch sizes. Topics that I would emphasize include the mechanics of the infeed loop constructor, how to monitor training and validation loss, how to build data sets efficiently, and how to profile a model that has been deployed to the IPU using the various tools provided in the SDK. Please note that additional resources and tutorials can be found in our developer portal. I hope you have found this session useful and informative.